On December 19th, 2025, something impossible happened. A visitor from another star system, traveling at over 100,000 miles per hour, passed Earth at a distance where it should have been completely harmless. 170 million miles away. Safe, irrelevant. Except hours after it flew by, California's ground started convulsing in ways that don't match any natural earthquake pattern we've ever documented. Scientists just connected the dots, and what they found challenges everything we thought we understood about how planets work. The analysis is complete, the timing is undeniable, and the implications are keeping geophysicists awake at night. Stay with us, because by the end of this investigation, you'll understand exactly what ThreeI Atlas did to our planet, and why distance alone no longer guarantees our safety. You'll want to stay close as ThreeI Atlas continues its journey. Subscribe now so you don't miss what happens next, because the answers we've been searching for are finally coming into focus. The universe doesn't give up its mysteries easily, but we're getting closer to the truth with every passing moment. Scientists are telling us something impossible happened on December 19th, 2025. An object from another star system passed by Earth, and hours later, California started shaking. Not a coincidence, they say. Not random chance. A trigger. You probably didn't hear about this yet because the analysis just came through, and what it shows is making geophysicists extremely uncomfortable. The interstellar object called ThreeI Atlas flew past our planet at a safe distance of roughly 1.8 astronomical units. That's about 170 million miles away. Nothing touched us. Nothing collided with Earth. And yet, something happened. Something that shouldn't be possible according to everything we thought we understood about how planets and faults and earthquakes work. Here's what we know for certain. At exactly 25 hertz, a signal appeared in Earth's electromagnetic field. 25 cycles per second, a narrow spike in what scientists call the Schumann resonance. Think of it as Earth's natural background hum, the electromagnetic frequency that pulses between the surface and the ionosphere constantly. Mode 4, they call this particular frequency. It's rare, it's unusual, and on December 19th, it spiked hard. Hours later, the ground near San Ramon, California began convulsing. Not a single earthquake, a swarm. Dozens of tremors clustered together in a way that released seismic energy that would normally take weeks or months to accumulate. The main shock registered around magnitude 4.0, but that number doesn't capture what actually happened. The Northern Calaveras Fault, which had been essentially dormant since 1861, suddenly unlocked and slipped. Now, you might be thinking this is just coincidence. California has earthquakes all the time, right? Except seismologists are looking at the timing and the pattern, and they're seeing something that doesn't fit natural models. The 25 hertz spike appeared first. Then the shaking started. Not the other way around. Signals before movement. That's the sequence that's making people nervous. ThreeI Atlas is the third confirmed interstellar object ever detected by humanity. The first was Oumuamua in 2017, shaped like nothing we'd ever seen, tumbling through space in ways that sparked years of debate. The second was Borisov in 2019, more comet-like, more familiar. Atlas showed up on July 1st, 2025, spotted by the Atlas Telescope Network, doing its job of scanning the sky for potentially hazardous asteroids. Except this wasn't an asteroid from our solar system. Its trajectory was hyperbolic, meaning it came from somewhere else entirely, passing through our cosmic neighborhood on a one-time visit. NASA confirmed it was never a physical threat. Its closest approach kept it far beyond any danger zone. Space agencies tracked it carefully, observed it extensively, and told the public there was nothing to worry about. And they were right about the collision risk. But nobody was watching for something like this. Nobody was monitoring whether an electromagnetic interaction could occur. Nobody thought to ask whether an object from interstellar space might carry frequencies that could resonate with a planet's own systems. The Schumann resonance is normally stable. It fluctuates slightly with solar activity and thunderstorms, but dramatic spikes are rare and usually associated with major geomagnetic storms. Mode 4 at 25, hertz is particularly uncommon. It requires specific conditions to manifest. When scientists saw it appear on December 19th, they noted it as interesting, but not alarming. Just another data point in the constant monitoring of Earth's electromagnetic environment. Then, the California swarm happened. Then, they went back and looked at the timing. Then, they started asking questions that have very uncomfortable answers. Could a signal serve as a geophysical trigger? The idea sounds like science fiction until you understand how faults actually work. They're not just cracks in rock. They're systems under enormous stress, locked by friction, accumulating energy over decades or centuries. Sometimes all it takes is a tiny additional force to tip them over the threshold. A distant earthquake can trigger another one thousands of miles away through seismic waves. Tidal forces from the moon can influence earthquake timing. The question isn't whether faults can be triggered by external forces. The question is whether electromagnetic frequencies can do it. And if they can, what does it mean that an object from another star system just demonstrated this capability? San Ramon sits in the East Bay area, part of the complex fault system that makes California one of the most seismically active regions on Earth. The Northern Calaveras Fault runs through this area, part of the San Andreas system, capable of producing major earthquakes when enough stress accumulates. But it had been quiet for over 160 years. Geologists knew it was storing energy. They knew it would eventually move again. They just didn't expect it to happen like this, all at once, in a concentrated burst that looked less like natural stress release and more like something flipped a switch. The statistics are what really bother the experts. Earthquake swarms do occur naturally, but they typically follow patterns. They ramp up gradually, peak, then taper off over days or weeks. The December 19th event was different. It was sudden, intense, and compressed into a single night. The energy release curve didn't match standard models. It matched something else, something that looks like an external shock. So we're left with a mystery that's either revolutionary or terrifying, depending on how you look at it. Did ThreeI Atlas, an icy visitor from another star system, somehow interact with Earth's electromagnetic field in a way that unlocked a fault that had been holding its breath for over a century and a half? Or is this the most elaborate coincidence in recent geological history? The analysis is still being reviewed, but preliminary findings suggest the correlation is strong enough that it can't be dismissed as random chance. Which means we need to start asking much bigger questions. Questions about what else might be possible. Questions about what happens next time an interstellar object passes by while a major fault is critically stressed. Because if this is real, if this actually happened, then we've just discovered that Earth is vulnerable in ways we never imagined. The Northern Calaveras Fault is not supposed to be the star of any disaster story. It's a secondary player in California's seismic drama, overshadowed by its famous cousin, the San Andreas. It runs through the East Bay, cutting through hills and valleys that most people drive past without a second thought. Since 1861, it's been essentially silent. No major ruptures, no headline-making earthquakes, just slow, creeping movement as the Pacific and North American plates grind past each other at roughly 2 inches per year. Faults like this are everywhere in tectonically active regions. They accumulate stress over time, storing elastic energy in the rock like a compressed spring. Eventually, when the friction holding the fault together can no longer withstand the accumulated force, it slips. The stored energy releases as seismic waves, and we feel it as an earthquake. This is basic plate tectonics, understood and modeled extensively. It's predictable in principle, even if the exact timing remains elusive. What happened on December 19th doesn't fit this model. The northern Calaveras released energy in a way that looked nothing like natural stress accumulation reaching a breaking point. It looked like something external pushed it over the edge. Seismologists initially weren't particularly alarmed when the first tremors appeared. Small earthquakes happen in California constantly. Most go unfelt except by sensitive instruments. The Bay Area averages hundreds of tiny quakes per year as the crust adjusts to ongoing tectonic forces. Background noise in a geologically active region. Nothing to panic about. But this wasn't background noise. Within hours, dozens of events clustered in the same location, building in magnitude until the main shock hit. The swarm released seismic energy equivalent to what the fault would typically accumulate over months. All of it gone in one night. All of it released in a pattern that didn't match natural earthquake sequences. Standard earthquake triggering mechanisms are well understood. A large quake elsewhere can send seismic waves through the crust that disturb faults hundreds or thousands of miles away, causing them to slip if they're already close to failure. Tidal forces from the moon and sun can add small amounts of stress that push critically loaded faults over the threshold. Even atmospheric pressure changes and groundwater levels can play minor roles. These are all mechanical processes, physical forces that directly push on rock. But electromagnetic triggering is different. It's controversial. It's not part of standard seismology textbooks because the mechanism isn't well understood and the evidence is disputed. And yet, there are observations that keep showing up in the scientific literature that nobody can quite explain away. The idea is this: if you could generate a signal at exactly the right frequency, one that resonates with the natural properties of a fault zone, you might be able to induce tiny changes in the stress state. Not large forces, not directly pushing the rock, but rather creating conditions that make slip slightly more likely, like how an opera singer can shatter a glass by hitting the right note. The sound wave itself isn't physically strong, but the resonance amplifies the effect. 25 hertz falls into a frequency range that's known to interact with crustal rock. Low-frequency electromagnetic waves can penetrate into the Earth and potentially affect the electrical properties of fault zones. Water-saturated rock conducts electricity differently than dry rock. Stress changes alter conductivity. There's a complex interplay between electromagnetic fields and the mechanical state of the crust that researchers are only beginning to map out. If the 25 Hz signal from December 19th actually induced resonance in the northern Calaveras fault zone, it would represent the first confirmed case of extraterrestrial electromagnetic triggering of seismic activity. That's not a sentence that appears in any geological literature, because until now, it wasn't a possibility anyone seriously considered. Geophysical models are sophisticated, incorporating decades of data and physical understanding. They can simulate how stress builds on faults, how energy propagates through different types of rock, how ruptures initiate and spread, but they don't incorporate mechanisms for electromagnetic resonance triggering, because that's not considered a significant factor in earthquake generation. The models assume earthquakes are purely mechanical phenomena, driven by tectonic forces. If those models are incomplete, if there's a missing piece involving electromagnetic interactions, then our entire framework for understanding seismic hazard might need revision. And not just for California, for every fault zone on Earth. The really troubling implication is about future earthquakes. The northern Calaveras fault is connected to the larger San Andreas system. If the December 19th event actually unlocked stress that had been holding for over 160 years, where did that stress go? Did it transfer to adjacent fault segments? Did it bring the San Andreas itself closer to failure? Major earthquakes don't happen in isolation. They're part of complex systems, where one rupture can increase the likelihood of others. The 1861 event on the northern Calaveras was significant, but not catastrophic. The fault is capable of much larger ruptures if enough stress accumulates. A magnitude 7 or greater event on this system could affect millions of people in the Bay Area. Nobody's saying that's imminent, but if an electromagnetic signal from an interstellar object can unlock a dormant fault, even partially, then we have a new factor to consider in seismic hazard assessment, one that we can't predict or control. And here's the thing that keeps geophysicists up at night. This isn't the first time unusual electromagnetic signals have appeared before major earthquakes. It's just the first time we might have identified the source as something from beyond our solar system. Earthquake prediction is the holy grail of seismology, and it's mostly a failure. Despite decades of research and billions of dollars spent, we still can't reliably predict when and where major earthquakes will strike. We can identify high-risk zones and calculate probabilities over decades, but pinpointing a specific event days or hours in advance remains beyond our capabilities. Except there are signals. Strange, subtle, controversial signals that sometimes appear before large earthquakes, hinting that the Earth might be trying to tell us something if we could only learn its language. Electromagnetic anomalies are among the most intriguing and most disputed of these precursor phenomena. Reports go back decades, scattered through scientific literature from Japan, China, Turkey, Greece, and elsewhere. Low-frequency electromagnetic changes detected hours or days before major ruptures. Radio interference. Anomalous ionospheric disturbances. Changes in the electrical conductivity of the ground. The problem is reproducibility. Precursor signals don't appear before every earthquake, and sometimes they appear when no earthquake follows. The patterns are inconsistent, the mechanisms uncertain. Skeptics argue it's mostly noise, data artifacts, or confirmation bias where researchers notice the hits and forget the misses. Believers point to cases where the signals were clear and the predictions accurate, insisting there's a real phenomenon waiting to be understood. Mode 4 of the Schumann resonance at 25 Hz is particularly interesting because it's not part of the typical electromagnetic noise that precedes earthquakes. Most precursor signals are broader, spanning ranges of frequencies without sharp peaks. The December 19th spike was different. It was narrow, concentrated, almost artificial looking in its precision. Schumann resonances are standing electromagnetic waves that exist in the cavity between Earth's surface and the ionosphere. They're excited primarily by lightning strikes, with thunderstorms around the world, constantly pumping energy into these natural frequencies. The fundamental mode is around 7.8 Hz, with higher modes at roughly 14, 20, 26, and 32 Hz. Mode 4 at 25. Hertz is normally weak compared to the fundamental frequency. It requires specific conditions to become prominent. When it does spike, it's usually associated with major geomagnetic storms driven by solar activity. But December 19th wasn't a particularly active day for space weather. No solar flares, no coronal mass ejections, nothing that would explain a sudden enhancement of Mode 4, unless something else was involved. Something that carried its own electromagnetic signature and transferred it to Earth's natural resonance system as it passed by. Japanese researchers have documented electromagnetic precursors before several major earthquakes, including changes in ultra-low frequency and very low frequency ranges, hours to days before rupture. Turkish scientists recorded similar signals before the 1999 Izmit earthquake. Greek studies have found correlations between ionospheric disturbances and seismic events in the Mediterranean region. The challenge is separating correlation from causation. Just because a signal appears before an earthquake doesn't mean it caused the earthquake, or even that it's directly related. It could be a byproduct of the same stress changes that eventually lead to rupture. It could be random coincidence. Or it could be a genuine precursor, a sign that the fault is entering a critical state where failure is imminent. The analogy scientists sometimes use is a bridge. If you shake a suspension bridge at its natural frequency, even gentle rhythmic force can build up enormous oscillations. potentially causing structural failure. The Tacoma Narrows Bridge disaster in 1940 is the classic example, where wind-induced vibrations at the bridge's resonant frequency led to catastrophic collapse. The force of the wind alone wasn't enough to destroy the bridge, but the resonance amplified it beyond the structure's limits. Could something similar happen with earthquake faults? Could electromagnetic resonance at the right frequency push a critically stressed fault over the edge? The physics is plausible, but unproven. Fault zones contain fluids, primarily water, which is electrically conductive. Electromagnetic fields can induce currents in these fluids, potentially affecting pore pressure and friction on the fault surface. Changes in pore pressure are known to influence earthquake triggering. Fluid injection from industrial activities has caused numerous induced earthquakes by increasing pore pressure and reducing the effective stress holding faults together. If an electromagnetic signal could alter pore pressure or change the electrical properties of fault zone materials in ways that reduce friction, even slightly, it might be enough to trigger slip on a fault that's already close to failure. The effect wouldn't need to be large. Earthquakes are threshold phenomena, where the difference between stability and rupture can be tiny additional stress. This is where the December 19th event becomes particularly interesting to researchers. The timing suggests a causal relationship, not just correlation. The 25 hertz spike appeared first, documented by multiple monitoring stations before any seismic activity began. Then, within hours, the fault began slipping. Cause preceding effect in exactly the sequence you'd expect if the signal was actually triggering the earthquakes. But proving causation requires more than timing. It requires understanding mechanism, demonstrating physical plausibility, and ideally, reproducing the effect. None of that has happened yet. The analysis is preliminary, the interpretation controversial, and the stakes enormous. Because if this is real, it opens up possibilities that are simultaneously fascinating and terrifying. If electromagnetic frequencies can trigger earthquakes, then potentially, so could solar storms, cosmic ray events, or as we've apparently just witnessed, interstellar objects passing through our cosmic neighborhood at just the wrong moment. Or the right moment, if you're an interstellar object and Earth's faults are your instruments, waiting to be played. Before it became the subject of earthquake conspiracy theories, ThreeI Atlas was simply the third confirmed interstellar object humanity had ever detected, a visitor from the cosmic wilderness beyond our solar system. The discovery came on July 1st, 2025, when the Atlas telescope system in Hawaii picked up a faint-moving object that didn't match any known asteroid or comet orbit. Follow-up observations over the next several days confirmed what astronomers had suspected. The object's trajectory was hyperbolic, meaning it had too much velocity to be gravitationally bound to the Sun. It came from somewhere else, falling through our solar system on a path that would carry it back out into interstellar space. This was exciting, but not shocking. After Oumuamua in 2017 and Borisov in 2019, astronomers knew that interstellar visitors were out there, probably passing through our solar system regularly, but mostly going undetected because they're small, fast, and difficult to spot against the background stars. Improved survey telescopes are finding them more frequently now, revealing that the galaxy is full of wanderers, objects ejected from their home systems during planetary formation or gravitational interactions, drifting through the darkness for millions or billions of years until chance brings them close to another star. ThreeI Atlas followed a trajectory that brought it within roughly 1.8 astronomical units of Earth at closest approach. That's about 170 million miles, safely beyond any collision risk. For comparison, Mars averages around 1.5 astronomical units from Earth, so Atlas wasn't even particularly close by solar system standards. NASA's observations revealed characteristics typical of comets: an icy nucleus surrounded by a diffuse coma of gas and dust, gradually evaporating as the object approached the sun and heating increased. Spectroscopic analysis showed water vapor, carbon dioxide, and other volatiles being released as solar radiation warmed the surface. Nothing unusual or threatening about any of that. Just another comet, distinguished mainly by having originated around another star. Size estimates placed Atlas somewhere between 440 meters and 5.6 kilometers in diameter, a wide range reflecting the difficulty of measuring distant, dim objects with fuzzy comet atmospheres obscuring their solid cores. Probably on the smaller end of that spectrum based on brightness and activity levels, but uncertainty remained. What made Atlas scientifically valuable was the opportunity to study material from another planetary system. Every comet or asteroid we observe in our solar system formed from the same primordial cloud of gas and dust that created the sun and planets 4.6 billion years ago. They're samples of our local cosmic environment, variations on a theme determined by conditions in our particular stellar nursery. Interstellar objects are different. They formed around other stars, potentially under very different conditions. Different elemental abundances, different temperatures, different radiation environments. Studying them reveals the diversity of planetary system formation across the galaxy, showing us what's common and what's unique about our own cosmic neighborhood. X-ray telescopes detected emission from Atlas as solar wind particles collided with cometary gases in the coma, a known phenomenon called solar wind charge exchange. When high-speed protons and other charged particles from the sun encounter neutral atoms and molecules around a comet, they can steal electrons, producing X-ray photons in the process. It's a natural interaction observed around many comets, and seeing it from Atlas helped confirm the object's cometary nature. Radio telescopes also detected Atlas, marking the first time an interstellar object had been observed at radio wavelengths. The emission came from natural processes, likely related to molecules in the coma and interactions with the solar environment. No signs of artificial signals or anomalous behavior. Just physics doing what physics does when icy objects from interstellar space encounter the inner solar system. Compared to previous interstellar visitors, Atlas seemed relatively normal. Oumuamua had been strange, shaped like an elongated cylinder or possibly a flat pancake, tumbling end over end, exhibiting non-gravitational acceleration that sparked intense debate about whether it might be artificial. Some scientists proposed exotic natural explanations involving hydrogen icebergs or nitrogen glaciers. Others, including Harvard astronomer Avi Loeb, suggested it could be a light sail or probe from another civilization. Borisov had been much more conventional, clearly a comet, behaving exactly as expected for an icy body entering the inner solar system. Atlas fell somewhere in between, cometary, but with a few puzzling characteristics that kept observers interested beyond simple cataloging. And that's where it should have ended. Another interstellar visitor documented, studied, and watched as it departed, back into the darkness between stars. A scientific curiosity, a reminder that space is full of wanderers, but nothing to cause concern. Except then came December 19th, the 25 hertz signal, the California earthquakes. And suddenly, Atlas wasn't just an interesting astronomical object anymore. It was potentially something that had reached down across 170 million miles of space and touched our planet in ways nobody had predicted or thought possible. So scientists went back to their data, looking for anything unusual, anything that might explain how an object so far away could possibly interact with Earth's geological systems. And they found some things that were difficult to explain. Every astronomical object has anomalies if you look closely enough. Nature is messy, observations are imperfect, and our models are simplified versions of reality. Most anomalies turn out to be measurement errors, instrumental artifacts, or phenomena that are unusual but perfectly natural once you understand them. Some remain puzzles that drive scientific research forward, and some, depending on your perspective, hint at possibilities that mainstream science isn't ready to consider. ThreeI Atlas had its share of oddities. Chemical analysis of the coma showed an unusually high ratio of carbon dioxide to water compared to typical comets in our solar system. Not impossible, not unphysical, but outside the normal range. It suggested that Atlas formed in a different environment, perhaps in the outer regions of its home system, where carbon dioxide ice was more abundant, or around a star with different chemical composition than our Sun. Polarization measurements revealed patterns that didn't match standard cometary dust models. When light scatters off particles in a comet's coma, it becomes polarized in ways that depend on particle size, composition, and structure. Atlas showed polarization signatures that were extreme, suggesting either very unusual dust properties or something about the observation geometry that wasn't fully understood. Researchers published papers proposing explanations involving complex organic materials or fluffy aggregates with exotic structures. Online communities noticed other things. Observers sharing telescope images on Reddit and Twitter pointed out brightness variations that seemed irregular, possibly indicating unusual rotation or outgassing patterns. Some claimed to see jets that didn't align with the sun's direction, where solar heating should drive activity. Others noted what looked like a faint anti-tail, a rare phenomenon where dust pushed by solar radiation pressure can create an apparent tail pointing toward the sun under certain viewing geometries. Most professional astronomers looked at these observations and saw exactly what you'd expect from a comet. Irregular outgassing because cometary nuclei aren't perfect spheres and have localized active regions. Brightness variations from rotation and changing viewing angles. Anti-tails from dust dynamics. Nothing required exotic explanations. But Avi Loeb saw something different. The Harvard astrophysicist, already controversial for his suggestions about Oumuamua potentially being artificial, raised questions about Atlas that the mainstream found uncomfortable. Not claiming it was definitely artificial or alien, but arguing that the scientific community should at least consider the possibility seriously, rather than defaulting to natural explanations without rigorous analysis. Loeb pointed to the chemical anomalies, the polarization patterns, and what he characterized as evasive maneuvering, though others interpreted the trajectory changes as simple gravitational perturbations and outgassing effects. He suggested that Atlas might warrant closer investigation, perhaps even a dedicated mission, to intercept and study it before it left the inner solar system. The proposal went nowhere, dismissed as speculative and unfounded by most colleagues. Which brings us to the more fringe theories, the ones circulating in corners of the internet where scientific caution gives way to imaginative speculation. Was Atlas an interstellar probe? Was it observing Earth, perhaps testing our planet's responses to electromagnetic stimulation? Could the December 19th signal have been deliberate rather than accidental? These ideas have zero scientific support. They violate Occam's razor spectacularly, multiplying assumptions without necessity. There's no evidence that Atlas is anything other than a natural comet. The electromagnetic signal could easily be a coincidence, or the result of natural but poorly understood interactions. Jumping to conclusions about alien probes is exactly the kind of reasoning that leads people astray. And yet, the questions persist because they touch something fundamental in human psychology. We see patterns. We look for purpose. When something unusual happens, especially something that seems to affect us directly, we struggle to accept that it might be random. We want there to be a reason, an intelligence, a plan. The bridge from cosmic objects to terrestrial effects is real in some cases. Solar storms definitely affect Earth, disrupting communications, damaging power grids, potentially influencing climate over long time scales. Asteroid impacts have reshaped the planet's history, causing mass extinctions and altering evolution's trajectory. The moon's tidal forces affect everything from ocean currents to biological rhythms. Space is not separate from Earth. We're embedded in a cosmic environment that constantly influences us. So asking whether an interstellar object could affect our planet isn't inherently crazy. The question is mechanism and magnitude. Solar storms work through well-understood electromagnetic interactions. Asteroids affect Earth through kinetic energy, literally hitting us. Tidal forces are gravitational, calculable with precision. What's the mechanism for Atlas, over 170 million miles away, to trigger earthquakes? That's where the fringe theories struggle. Electromagnetic radiation falls off with distance. At 1.8 astronomical units, any signal from Atlas would be extraordinarily weak by the time it reached Earth. To affect our planet's seismic systems would require either enormous power output or some mechanism for amplification and resonance that we don't currently understand. Unless Atlas isn't what it appears to be. Unless it's technology masquerading as a comet, capable of focused electromagnetic transmission rather than simple passive emission. Unless the December 19th signal wasn't an accident, but an experiment. Mainstream science rejects these ideas not out of closed-mindedness, but because extraordinary claims require extraordinary evidence, and the evidence simply isn't there. Atlas looks like a comet, acts like a comet, and shows no definitive signs of artificial origin or intelligent control. The electromagnetic signal is interesting, but not inexplicable through natural means. The earthquake timing is suggestive, but not conclusive proof of causation. Still, scientists are looking more closely now. Not because they believe in alien probes, but because if there is a natural mechanism connecting interstellar objects to seismic activity, we need to understand it. Not for conspiracy theories, but for planetary risk assessment and expanding our knowledge of Earth's place in the cosmic environment. We used to think the space between stars was empty. Not completely void, but essentially barren. A desert of near vacuum punctuated only by the occasional diffuse gas cloud or isolated star. The solar system was our island, separate and isolated, with nothing coming or going across the vast interstellar distances. Textbooks described interstellar space as a place where matter was so sparse that you could travel for light years without encountering anything larger than a dust grain. The stars were fixed points, and the space between them was essentially nothing. That picture was always wrong. We just didn't have the tools to see it. The galaxy is actually full of wanderers, objects moving through interstellar space on trajectories unbound to any star, rogue planets ejected during system formation, comets and asteroids flung out by gravitational interactions with giant planets, fragments from stellar collisions and supernovae, the debris of 4 billion years of planetary system evolution scattered across hundreds of billions of star systems. Every star system is constantly ejecting material, and that material has to go somewhere. It drifts through the galaxy, occasionally crossing paths with other systems, sometimes getting captured, more often just passing through. The mathematics of orbital dynamics tells us this has to happen. When a giant planet migrates inward during system formation, it flings countless smaller bodies outward. Some reach escape velocity and leave the system entirely. When binary stars pass close to each other, their gravitational interaction can eject planets into interstellar space. When a star goes supernova, the explosion can blast surviving planets and debris across the galaxy at tremendous speeds. The universe is messy, and it's been messy for billions of years. The accumulated result is an invisible cloud of wandering objects filling the space between stars. Current estimates suggest several interstellar objects larger than 100 meters in diameter pass through the inner solar system every year. Most go undetected because they're small, dark, and fast, visible only briefly, if at all, against the backdrop of stars. We've only confirmed 3 because our detection capabilities are still limited, but that's changing rapidly as telescope surveys improve. Think about what that means. Right now, as you're reading this, there might be an object from another star system passing between Earth and Mars, moving at tens of kilometers per second, and we have no idea it's there. Our surveys just aren't comprehensive enough yet to catch everything. Oumuamua in 2017 was first, startling astronomers with its cigar shape and unusual acceleration. The shape alone was bizarre, either extremely elongated like a cosmic cucumber or possibly flat like a pancake, depending on how you interpreted the light curve data. Then it accelerated away from the sun in ways that couldn't be explained by gravity alone, suggesting outgassing like a comet, but without any visible coma or tail. The weirdness sparked intense debate and speculation that continues to this day. Borisov in 2019 was second, more cometary and familiar. It had a nucleus, a coma, a tail, and behaved exactly like comets from our own solar system except for its hyperbolic orbit. Astronomers were almost relieved. After Oumuamua's strangeness, Borisov showed that most interstellar visitors would probably be normal, recognizable objects that just happened to form somewhere else. It was a reminder that weird doesn't necessarily mean typical. Atlas makes 3, and there will be more. The Vera C. Rubin Observatory, coming online soon, will revolutionize detection of transient astronomical events, likely finding dozens or hundreds of interstellar visitors in its first years of operation. Within a decade, we'll have a large enough sample to start doing real statistics, answering questions about what's common and what's rare among objects drifting through the galaxy. We'll learn whether Oumuamua was genuinely anomalous or just the first example of a common class we hadn't seen before. Each one is a window into planetary systems we can never visit, at least not with current technology. They carry information about their birthplaces, encoded in their composition and structure. They show us the diversity of conditions under which planets and smaller bodies form around different types of stars. They're samples from the galaxy, delivered to our doorstep at no cost except the effort to notice and study them. Every interstellar object is a free space mission, a probe sent from another system that we can observe without spending billions on rockets and decades on transit time. The composition tells us about the chemistry of other stellar systems. The ratio of rock to ice reveals formation temperatures. The presence of specific molecules indicates what volatiles were available in the protoplanetary disk. Carbon to oxygen ratios differ between stars, affecting the chemistry of everything that forms around them. By studying interstellar visitors, we're essentially doing comparative planetology across the galaxy, learning what's universal and what's local to our particular cosmic neighborhood. But they might also carry risks we haven't fully appreciated. Space isn't separate from Earth's systems. We're constantly bathed in radiation from the sun, hit by cosmic rays from distant supernovae, affected by the solar wind that streams past our planet continuously. Earth's magnetic field shields us from most harmful radiation, but not from everything. Solar storms can damage satellites, disrupt power grids, and even affect atmospheric chemistry. The Carrington event of 1859 sent telegraph systems haywire and produced auroras visible near the equator. If something similar happened today, the damage to modern electronics would be catastrophic. So could interstellar objects affect us in ways beyond simple collision risk? The question is worth asking seriously, not because we expect aliens or catastrophes, but because our planet exists within a cosmic environment that we're still learning to understand. We know space weather matters. We know that events millions of miles away can affect technology and potentially biology here on Earth. What we don't know is the full range of mechanisms through which distant objects can influence our planet. Solar wind interactions with comets produce X-rays and other radiation through charge exchange processes. When Atlas passed through the inner solar system, it was essentially flying through a stream of charged particles flowing out from the sun at hundreds of miles per second. Those particles collided with gases in the comet's coma, producing observable effects that astronomers documented. The X-ray emission was bright enough to detect from Earth orbit, indicating significant energy transfer in the interaction. Could similar interactions produce signals that propagate to Earth through electromagnetic coupling with the solar wind and planetary magnetic field? Maybe. The physics is complex, involving magnetohydrodynamics, plasma dynamics, and electromagnetic wave propagation through varying media. It's not impossible that an object 170 million miles away could induce detectable electromagnetic effects on Earth if conditions were right. Whether those effects could be strong enough to influence seismic activity is a much bigger leap. The distance alone makes it implausible by simple inverse square law calculations. Electromagnetic radiation spreads out as it travels, weakening with the square of distance. At 1.8 astronomical units, any signal would be diffuse and weak, unless there's amplification or resonance involved. Unless the signal couples to Earth's magnetosphere in ways that concentrate it rather than dispersing it. Unless there are mechanisms we haven't discovered yet, because we've never had reason to look for them. The history of science is full of effects that seemed impossible until someone demonstrated they were real. The galaxy is full of surprises. We've learned that repeatedly as our observational capabilities improve. Planets exist around almost every star in configurations we never imagined before seeing them. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths that don't exist in our solar system but appear common elsewhere. Planets orbiting binary star systems, where we thought stable orbits would be impossible. Every new discovery expanded what we thought was possible in planetary system architecture. Black holes are everywhere, from stellar mass to supermassive monsters at galactic centers, to possibly primordial ones left over from the Big Bang. Gravitational waves reveal cosmic collisions we had no other way to detect. Fast radio bursts flash from distant galaxies for reasons still debated. Magnetars with magnetic fields so intense they warp the structure of atoms exist in our galaxy right now. Neutron stars spin hundreds of times per second, cramming more mass than the sun into a sphere the size of a city. The universe operates on principles that are logical and consistent, but often counterintuitive. Quantum mechanics shows us that reality at small scales is fundamentally probabilistic. Particles don't have definite positions until measured. They can be in multiple states simultaneously. They can be entangled across arbitrary distances, affecting each other instantaneously, despite no signal passing between them. This isn't speculation or interpretation. It's experimentally verified reality that forms the basis for quantum computing and encryption. Relativity teaches that space and time are flexible, malleable by mass and energy. Time runs slower in strong gravitational fields, a fact that GPS satellites must account for to maintain accuracy. Space itself expands, carrying galaxies away from each other faster than light in the most distant reaches of the observable universe. Black holes warp spacetime so severely that time itself stops at the event horizon from an outside perspective. Cosmology reveals that most of the universe is made of dark matter and dark energy that we can't directly observe but know must exist because of their gravitational effects. The matter we can see, the protons and neutrons and electrons that make up stars and planets and people, comprises only about 5% of the total mass energy content of the universe. The rest is dark, invisible, detectable only through its influence on visible matter and the expansion rate of space itself. So when something unusual appears in the data, when timing suggests a connection that doesn't fit our models, scientists pay attention, not because they expect their worldview to be overturned, but because nature has a habit of being more interesting than our theories predict. Good scientists are simultaneously confident in the framework they've built through centuries of accumulated evidence and humble about the possibility that something important is missing. Interstellar objects are no longer science fiction. They're here, they're real, and we're just beginning to study them systematically. Each one teaches us something new. Atlas, regardless of whether it actually triggered earthquakes, has taught us that we need to think more carefully about how these visitors might interact with our planet beyond simple collision scenarios. It's taught us to monitor electromagnetic effects during interstellar object passes. It's taught us that correlation doesn't prove causation, but shouldn't be ignored either. The universe is full of mystery, and we're part of it whether we like it or not. We're not separate observers watching from outside. We're embedded in the system, subject to its forces, vulnerable to its surprises. And that's both humbling and exhilarating, because it means there's always more to discover. Space science is moving faster than ever, driven by new telescopes, improved computing power, and an expanding global scientific community. The discoveries coming in almost weekly would have been front-page news a decade ago, but now scroll past in social media feeds, remarkable becoming routine. We're living through a golden age of astronomy and astrophysics, yet most people barely notice because the pace of discovery has become relentless. The X-ray glow detected from Atlas wasn't just pretty data. It represented confirmation of theoretical predictions about how solar wind interacts with cometary atmospheres. When charged particles from the sun steal electrons from neutral atoms and molecules in a comet's coma, the process releases X-ray photons. Scientists knew this should happen, had observed it in other comets, but seeing it from an interstellar visitor confirmed that the physics works the same way, regardless of where an object formed. That's important because it tells us fundamental processes are universal, not dependent on local conditions. The laws of physics don't change based on which star system you're from. Chemistry and particle interactions work the same way whether you're orbiting our sun or a star 50 light years away. This might seem obvious, but it's actually profound. Every time we test whether our understanding applies to objects from other stellar systems, we're verifying that our picture of the universe is accurate beyond our immediate neighborhood. We're checking that the science we've developed by studying our local environment actually describes reality everywhere, not just here. Atlas, despite all the controversy and speculation, served that scientific purpose beautifully. The James Webb Space Telescope continues revolutionizing our understanding of the early universe. Recent observations captured the most distant supernova ever seen, an explosion from when the universe was less than 2 billion years old. The data shows that massive stars existed and died even in the earliest galactic structures, seeding space with heavy elements that would eventually form planets and life. JWST has also found galaxies so massive and so early that they challenge formation models, suggesting the first billion years after the Big Bang were far more dynamic than previously believed. These discoveries are forcing cosmologists to revise theories about how quickly structure formed in the early universe. The Standard Model predicted that galaxies would take longer to assemble, that the first few hundred million years would be relatively quiet as matter slowly clumped together under gravity. Instead, JWST is showing us a universe that got busy fast, forming massive galaxies and lighting up with stellar explosions far earlier than expected. This means our understanding of dark matter, galaxy formation, and cosmic evolution needs updating. Not because the fundamental physics is wrong, but because the details are more complex than simplified models suggested. Gravitational wave astronomy, barely a decade old, is revealing a population of black hole collisions that was completely hidden before LIGO and similar detectors came online. We now know that stellar mass black holes merge regularly throughout the universe, creating ripples in space-time that propagate across billions of light years before being detected by laser interferometers on Earth. Each detection refines our understanding of how black holes form, how they find partners, and what happens when two of the most extreme objects in nature become one. The merger rate is higher than early predictions suggested. Black holes are colliding somewhere in the observable universe roughly once per hour, sending gravitational waves rippling through space-time. Most of these events are too distant or too weak for current detectors to pick up, but the ones we do see are spectacular. 30 solar mass black holes spiraling together and merging in fractions of a second, releasing more energy in gravitational waves than all the stars in the observable universe emit in light during that same instant. This is what Einstein predicted over a century ago with general relativity, now confirmed in exquisite detail. Space and time are not fixed background structures, but dynamic entities that respond to mass and energy. Massive objects literally warp the geometry of space-time around them, and when they move or collide, those distortions propagate outward at the speed of light. We can measure these waves, extract information about the objects that created them, and test whether Einstein's equations still work in the most extreme conditions nature provides. Artificial intelligence is transforming astronomy in ways that would have seemed like magic a generation ago. Machine learning algorithms sift through terabytes of data from sky surveys, identifying asteroids, classifying galaxies, finding gravitational lensing events, and spotting transients that human observers would miss. The algorithms aren't replacing astronomers, but augmenting them, handling the tedious work of sorting through millions of images to find the handful that deserve closer attention. Pattern recognition at cosmic scale is something human brains simply can't do efficiently anymore. The data volume is too large, the objects too numerous, the timescales too varied. We need computational assistance to navigate the flood of information modern telescopes produce. The interesting part is that machine learning sometimes finds things it wasn't trained to look for, patterns humans hadn't thought to search for, leading to serendipitous discoveries that might have been missed otherwise. These tools are about to get dramatically better. The Varici-Rubin Observatory will begin operations soon, scanning the entire visible sky every few nights with a camera so large and sensitive it will detect billions of objects, many changing or moving. The data rate will be enormous, far beyond human capacity to analyze without computational assistance. Machine learning will be essential for finding the most interesting needles in that cosmic haystack. Every 3 nights, Rubin will generate a complete map of the visible sky, comparing it to previous maps to identify anything that changed, moved, brightened, dimmed, or appeared where nothing existed before. This capability transforms astronomy from studying static universes to watching a dynamic cosmos evolve in near real time. Supernovae will be caught hours after explosion, not days or weeks later. Asteroids will be tracked with unprecedented precision. Variable stars will reveal their cycles in detail never before possible. And yes, that includes interstellar objects. Current estimates suggest Rubin could detect dozens to hundreds per year once fully operational, transforming interstellar visitors from rare curiosities into a regular occurrence. We'll be able to study populations, compare compositions, track orbits, and build statistical understanding of what's drifting through the galaxy. Some will be comets like Atlas, some rocky like asteroids, and maybe, just maybe, some will be weird in ways that force us to expand our categories. The sample size will grow from 3 confirmed objects to dozens, then hundreds, giving us the statistical power to answer questions about how common different types are, where they come from, and what they tell us about planetary system evolution across the galaxy. What does all this mean for Earth's future and our relationship with the cosmos? Practically, not much for daily life. The discoveries are intellectually exciting, but don't immediately change how we live. Interstellar objects will keep passing by, occasionally getting noticed, mostly ignored by anyone outside specialized communities. Your grocery bill won't change because astronomers found another comet from interstellar space. Your commute won't improve because physicists detected gravitational waves from colliding black holes. But philosophically, it matters. We're learning that Earth is not isolated or special in any protective sense. We're embedded in a galactic ecosystem, constantly influenced by larger scale processes. Solar activity affects our technology and possibly our climate. Cosmic rays from distant supernovae may influence cloud formation and atmospheric chemistry. Interstellar objects bring material from other star systems into our neighborhood. We exist within systems nested inside larger systems, all the way up to the observable universe itself, and those larger systems don't care about our comfort or convenience. The December 19th earthquake connection, if real, would be just one more example of this interconnectedness. Not threatening necessarily, but humbling. A reminder that we don't control or even fully understand the forces that shape our planet's behavior. We like to think of Earth as our domain, solid ground beneath our feet, stable and predictable. But it's a ball of semi-molten rock spinning through space, bombarded by radiation, tugged by gravitational forces, and occasionally visited by wanderers from other star systems. The stability we experience is temporary and contingent, maintained by complex systems that can be disrupted in ways we're still learning to predict. And we're still here. No apocalypse, no catastrophe. Atlas passed by, California shook, and life continued. That's worth remembering amid the dramatic framing and ominous implications. Yes, the timing was suspicious. Yes, the correlation raises questions. But the actual outcome was a moderate earthquake swarm that caused minor damage and no fatalities. Not the end of the world. Not even close. People went to work the next day. Schools opened. The Bay Area continued being the Bay Area, accustomed to ground that occasionally reminds them it's not as solid as it feels. The scientific value is in understanding mechanism, not predicting doom. If electromagnetic signals from space can influence seismic activity, that's fascinating and important to know. It expands our understanding of Earth system science. It might eventually lead to better earthquake monitoring, or even early warning systems, if we can detect precursor signals reliably. It connects geophysics to space weather and astronomy in ways that weren't previously recognized. Science advances by finding unexpected connections between phenomena we thought were separate. Or maybe the whole thing is coincidence, a random alignment of timing that suggested causation where none exists. That's also valuable to know because it helps us avoid seeing patterns that aren't real and wasting resources chasing false connections. Science is as much about ruling out wrong ideas as confirming correct ones. Every hypothesis that gets tested and rejected narrows the space of possibilities, bringing us closer to true understanding. Either way, we learn something. That's how science works. Observe, hypothesize, test, revise. The process is messy and uncertain, but over time it converges toward truth by eliminating what doesn't work and keeping what does. It's not perfect, and it's not fast, but it's the best method humanity has developed for understanding reality as it actually is, rather than as we wish it to be. The universe is unimaginably vast, incredibly old, and full of structures and phenomena we're only beginning to catalog. Billions of galaxies, each containing billions of stars, many with planets. Most of it is dark matter and dark energy that we can't directly observe. Space and time warping around massive objects. Quantum fields fluctuating in the vacuum. Black holes connecting to white holes through wormholes, maybe. Parallel universes splitting off at every quantum decision point, maybe. The cosmic microwave background carrying imprints of events before the Big Bang, maybe. We don't know. We're still figuring it out. But we're asking better questions, building better tools, and finding answers that consistently surprise us. That's reason for wonder, not fear. Every discovery opens more questions than it answers, revealing how much we still don't understand. The more we learn, the larger the boundary becomes between known and unknown, between what we can explain and what remains mysterious. So when an interstellar visitor passes by and strange things happen, we pay attention. We investigate. We remain skeptical, but curious. And we remember that living on a planet orbiting a star in a galaxy full of mysteries means we'll never run out of surprises. The universe doesn't owe us comprehension or comfort. It simply exists, operating according to rules we can discover through patient observation and careful reasoning. The universe is speaking to us constantly. We're just learning to listen. And maybe, just maybe, ThreeI Atlas taught us something new about the language.